Hello everyone, welcome back to your favorite and India's most affordable learning platform, Physics Wallah. So in the last session of mechanical properties of fluids, we discussed the venturimeter concept and the questions related to the Bernoulli's principle, especially the tap water questions and aeroplane wing questions. So those kind of concepts are very important. So you should practice questions related to that. And then, so today we are going to deal with the lecture number 6 of mechanical properties of fluids or fluid mechanics. So where today's class we are going to concentrate on the velocity of Efflux, so Torricelli's law, and the viscosity concept. Okay, so as usual I just need your attention for the next 1 hour, guys. So just be with me, avoid all the disturbances around you, and at the end of the lecture it's very important to prepare your own short notes. And the competitive examinations are around, so plan your own strategy. So complete the backlogs, so complete the syllabus class 11th and class 12th simultaneously, attempt more mock tests, do previous year questions, and analyze yourself time to time. Okay, so it's very important. Chalo, so let's get into the today's topic with very high positive energy. So what's the speed of Efflux and Torricelli's law? See, here I am taking a open vessel. So the first we are going to see, this is a open vessel. It's a open vessel. So now in this vessel, so up to the brim I fill the liquid, so height h. This is a container which is of height h and the fluid is filled in it. So now here, as it is open, the pressure which is acting at the top is a atmospheric pressure. There is no other pressure, only atmospheric pressure will act. So now at a height small h from the surface of the water, so we made a small hole which is of cross sectional area A, right? So this is called the hole or orifice. Hole or orifice. Okay, chalo. So its cross sectional area is A. So now from here, so the water or the fluid comes out, so with a velocity v. So the velocity which is v. Now see here, so as the water goes out from here or the fluid goes out from this small cross sectional area A, so the water level or the fluid level decreases in this container. So this level decreases very slowly. So that's why I can consider, so the velocity at this place is 0 and velocity here let it be v2, which is equals to v. So consider this is a point 1, consider this is a point 2. So between these 2 points, can we apply the Bernoulli's principle? So consider the flow is steady and we are going to take the Bernoulli's principle here. So from Bernoulli's principle, so chalo, see here, so the pressure 1 plus half rho v1 square plus rho g h1 is equals to p2 plus half rho v2 square plus rho g h2 plus rho g h2. So then here I can write, so what's the pressure P1? So the P ATM. Yes, fine. So then here the velocity I can consider almost 0, so that's why this term will become 0 plus rho g h1. So let's consider this total height. So the total height is going to be h. Yes or no? So this h1 is going to be, this is the height. So now, so this h2, let me consider this is the baseline. Consider this is a baseline. So from this baseline I can consider this height will be 0. It is at a height h. Yes or no? So from this baseline, this water level is at a height h. Okay, and then as it is the baseline, the h2 will become 0. So this term also will become 0. So now P2 is again, here the pressure that acts is again the atmospheric pressure. When the fluid comes out from here, so what's the pressure which is acting here? Again the atmospheric pressure. So that's what I am writing here. So in place of this P2, so you can write P ATM plus half rho, what is the velocity 2 here, which is v again, so v square. So then, so P ATM cancel, rho gh is equals to half rho v square. So the fluid is same, so the densities gets cancelled. So I can write here, so send 2 to this side, v square is equals to 2gh. So then v is equals to root 2gh. Have you ever seen this equation? So in the kinematics we have studied. So for a freely falling body, with what velocity it hits the ground? So with v is equals to root 2gh, right? So the same formula you can also apply here. So this speed v is called the velocity of Efflux. So this speed v is called the velocity of Efflux. So that means the velocity with which, so the water will, the fluid will come out, so from a open vessel due to the atmospheric pressure, right? So this velocity of Efflux v is equals to root over 2gh. So what is this h, sir? Small h. So from how much height, so the vessel is, the orifice is made or hole is made. Clear, guys? Done? Now, so here one more important point. So to empty the whole vessel, so where the hole should be? To empty the whole vessel, so the hole should be at the bottom. If you have to empty the complete vessel, so the hole should be at the bottom. Done? Clear? Chalo. Good. So here one more thing. So we can also write the rate of flow. What is the rate of flow from here? So the cross sectional area into the velocity. So that point also I'll mention. So the rate of flow. So mostly they'll ask in the questions, what is rate of flow? So the rate of flow is nothing but, so the cross sectional area of the hole A into the velocity with which the fluid is coming from there. So which is V, A into V, right? Done, guys? Sure. So let's try to solve this question on your own, everyone. So the level of water in tank is 5 meters high. So the whole of area 1 centimeter square is made at the bottom of the tank. So the rate of leakage of water from the hole here, see here. So this is a container. So now the hole is made at the bottom. So the hole is made at the bottom. So this hole is of area 1 centimeter square, cross sectional area. Fine. The total height is going to be 5 meter. Fine. So then they are asking the rate of leakage of water from the hole. So what is the rate of leakage of water here? What is the rate of leakage of water? That means the rate of flow they are asking. So the rate of leakage of water. So which is equals to rate of flow. So rate of flow. Fine. So what is that rate of flow? So it's cross sectional area into, so the velocity with which the fluid is coming out. So the fluid comes out with a velocity v from here. Yes. So A into, so what is that v? Root 2gh. A into root 2gh. Done. So what is A? The cross sectional area. So 1 centimeter square converted to meter square. 1 into 10 to the power minus 4 into root 2 into what is g? Let's take g as 10 into what is height here? So 5, right? Chalo. So 1 into 10 to the power minus 4 into, so 20 into 5 root 100. So root 100 is 10 again. So 1 into 10 to the power minus 4 into 10. So which is equals to 10 to the power minus 3 meter cube per second. Yes. So 10 to the power minus 3 meter cube per second. So option A is the correct answer, guys. Done? Clear? Simple question. Chal. So let's move to the next one. So we have one more question here. So what's the question says? A small hole of cross section 2 mm square. So the area of cross section is, area of the hole is given, present near the bottom of a fully filled tank. So it's a fully filled tank. So open tank. So it's an open vessel. So of height 2 meters. So taking G as 10, the rate of flow of water through the open hole would be nearly, see here. So this is a container which is of height 2 meters. right? So here let's suppose, so the hole is made here, so the water comes out from here, so with some velocity v. So the area of the cross section here, it is given 2 mm square, right? So that means 2 into 10 to the power minus 3 whole square, so which is nothing but 2 into 10 to the power minus 6 meter square, right? So this is the cross sectional area, 2 into 10 to the power minus 6 meter square. So they are asking the rate of flow of water through the open hole. So the rate of flow they are asking. So the rate of flow, so direct formula, so which is equals to A into V, right? So what is A? The cross sectional area, 2 into 10 to the power minus 6, yes, into, so what is V? Root 2 GH. So at what height the hole is made? So at the bottom, so you can take the complete height of the vessel, so which is 2 meters. So then substitute the values, 2 into 10 to the power minus 6 into, so root 2 G10 height H2. So then I can write it as, so 2 into 10 to the power minus 6 into, so 1 2 will come out, so into root 10. So 2 into 2, 4 into 10 to the power minus 6. So this is root 10 means something around 3.1 or 2. So which I can take it as, so 12.4 into 10 to the power minus 6. So meter cube per second. 10 to the power minus 6, 12.4. So approximately I could see that. So 12.6 into 10 to the power minus 6. Option C is the closest one. Done guys? Clear? Chal. Good. So we have got one more question. So let's try this question on your own. So what's the question says here? A large open tank has 2 holes in the wall. Okay. So one is a square hole of side L at a depth y from the top, and the other is a circular hole of radius r at a depth 4y from the top. Okay. So when the tank is completely filled with water, so the quantities of water flowing out per second from both the holes are the same. So see here. So the quantities of water flowing out per second from the both the holes are same. That means the rate of flow from the both the holes is same. So then R is equals to, see here, interesting question. So let's try with the concept first. So this is a vessel, so which is a open vessel, a large open tank. This is a large open tank. So fine. So there are 2 holes in the wall. So one is a square hole of side L at a depth y. At a depth y, let's suppose here at this point, so the L, and it is at a height y. Fine. So and then, so and the other is a circular hole of radius r at a depth 4y. At a depth 4y, so we have, so the radius r of this hole, and it is at a height of 4y. Yes, chal. So then when the tank is completely filled with the water, the quantities of flowing out, the quantities of water flowing out per second from both the holes are the same. So the rate of flow is same. So that means A1 V1 is equals to A2 V2. So or else I'll write the hint. So the rate of flow from both the holes is same. From both the holes is same. Right? Chalo, done. So we have got the hint. So now can we solve this question? So what's the rate of flow from the first one? So let's say A1, so and the velocity V1 is equals to the second one, so A2, so the velocity V2. So now let's substitute the values. So consider this is the first hole, this one is the first hole, and this one is the second hole. So the first hole is of the cross section square, right? Square. So that means the area will become L square. The area will become L square because it is of the side L. So its area will be L square into, so what's the velocity with which the water comes out from there? So root 2g, it is at a height y. So the square hole is at a height y. And then next, so A2, so what's the area of this one? Pi r square I can write, the circular cross section, right? So pi r square. So into what is the velocity v2 guys? Velocity v2 root 2g common, and this whole is at a height of 4 into y. Fine, done. So now you can solve the question easily. L square is equals to, so root 2g gets cancelled. So here root y is left, which is equals to pi r square, or else root 2gy you can cancel it out. So directly root 2gy, so root 2gy gets cancelled. So L square is left here. So and then here pi r square into root 4, pi r square into root 4, done. So then I have got L square is equals to pi r square into 2. So root 4 is 2. So we need r is equals to, so what is the r value? So what is the r value? So I can write, so r square is equals to L square by 2 pi. From here r square is equals to L square by 2 pi. R is equals to, so square root of L square is L by root 2 pi. L by root 2 pi is the correct answer. So the option 1 I can see from here. L by root 2 pi. Clear? Understood? Chalo. Simple question. So next we have one more question. So what's the question says here? Try to understand the given question first. Water flows into a large tank with flat bottom at the rate of 10 to the power minus 4 meter cube per second. So water is also leaking out of the hole of area of cross section 1 centimeter square at its bottom. If the water is in, if the water height of the water in the tank remains steady, yes, here is a hint. So then this height is, yes. So first understand the question. So this is a container. So now water flows into a large tank with flat bottom at the rate of 10 to the power minus 4 meter cube per second. So this is the rate of flow. Yes. So then, so water is also leaking out of a hole of cross sectional area 1 centimeter square. So here the cross sectional area is 1 centimeter square. So which we can write it as 1 into 10 to the power minus 4 meter square area. So then fine. So if the height of the water in the tank remains steady, so this height of the water it is steady. So if the water is going out from here, still the water level is not decreasing. That's what they are saying in the question. So that means with another pipe, so there is the flow of water with whatever the rate of flow from this pipe is there. So the same rate of flow from this hole. Yes. So then only the water will come, the water will be steady in this. Yes or no? So the level remain same. So the inflow is equals to the outflow. So then only the water height remains same. Okay. So that's what I am writing here. So the rate of water flow in is equals to, so the rate of water flow is equals to rate of flows outside. Yes. So then only its height remains same. So what is the rate of flow they already gave? So 10 to the power minus 4 here. So the rate of inflow, the rate of water flows inside the water open tank is, so 10 to the power minus 4. So and from the hole, so we know that the rate of flow will be A into V. So the cross sectional area into the velocity with which water is going out. So done. We have to find, so the height h. Yes, easy. So 10 to the power minus 4 is equals to, so what's the cross sectional area? 1 into 10 to the power minus 4 is 10 to the power minus 4. So into root 2g h. Yes, done. So this will come out to be, so 10 to the power minus 4, 10 to the power minus 4 gets cancelled. So 1 is equals to root 2 into g is 10 into h. Sorry, into h. So from here I'll write, so this is, so 1 by, so this is root 20. Yes, is equals to root h. Root 20 into root h I am writing. So root 20 I sent it to this side. We need h, right? So square it on both the sides. H is equals to, so 1 by 20. So 1 by 20 means, so I can write 0.05 meters. 0.05 meters. So then if I multiply it with 100, so centimeters we required. So approximately 5 centimeters. Yes or no? So approximately 5.1 centimeters. You can choose the closest option. Done. Understood the procedure? Shall. Good. So note this down, everyone. So do we have one more question here? So no. So let's go for the next concept, that is range. So what is the range? Range is nothing but the maximum horizontal distance. So the range is a maximum horizontal distance, right? Basic concept, just understand carefully, that's it. Here the water or the fluid, whatever it is, so it is coming out from this hole at a velocity v, right? So then we have got what is the rate of flow also. So now it falls at some distance from this vessel. From this vessel it falls at some distance, right? So then, so what is this distance? Is nothing but the horizontal range. I can write, so this is nothing but the horizontal range. Yes. So now, so you already studied the projectile motion. So this fluid is making the projectile path. So it's moving in the x direction as well as it is moving in the y direction, right? So to find the range, so what I am doing is, so let's take its motion in x direction, in its motion in y direction, both the, first let's write in y direction and let's write in the x direction. That's it. So you'll get the range formula. So in y direction, its initial velocity uy is equals to 0 because the water is flowing only in the horizontal direction initially. So the initial velocity in the y direction is 0. So then what is the time taken? So the time taken is equals to, so root 2h by g. Yes or no? So root 2h by g. Chalo. So root into, so what is this height from ground? So it is at a height of, so h minus h. It is at a height of h minus h. So we can write here the height as h minus h by g. That's it. H minus h by g. So now let's go for the x direction. In the x direction, I am applying the equation Sx is equals to uxt plus half ax t square. So then what is the distance in the horizontal? The distance in the x direction is nothing but the horizontal range, which is equals to ux is nothing but velocity v. So horizontally the acceleration will become 0 and velocity v into the time t. So with what velocity it comes out? So with root 2gh into, so what's the time taken? So root over 2 into h minus h into h minus h by g. So root g gets cancelled. So we can write root 2 into, so 2 into h minus h. So here 1 2 will come out. So root into h minus h. So this is a range formula. So the range r is equals to 2 into h minus h. So therefore the range of the fluid is equals to 2 into root over h into h minus h. So where the capital H is the total height of the fluid and then h is where the hole is made. Clear guys? So this concept is clear, everyone? Done? Chal. So now let's go for the next concept. So we got the question here. So let's try this question. Figure shows 2 holes in a wide tank containing liquid in a common. So the liquid is same. So the water streams coming out of these 2 holes strikes the ground at the same point. So they both strike at the same point, means the range is same for both, right? So then the height of the liquid column in the tank is, so the hint that they gave is, so they strike the ground at the same point. So that means the range is same. Here the range is same. Done. So let's write the first one and the second one. The range of the first one is equals to the range of the second one. So the first hole is here and the second hole is here. So then what's the range formula? So 2 into root over, so h. So what is the h? So the first one is at a height of 4 into, so the capital H is a total height. So answer is in centimeters. So let's put the values in centimeter itself. So then, yes or no? So R is equals to 2 into root over h into h minus h. So then that's what I am writing here. So h is 4. The first hole is made at a height of 4 centimeters. Small h is 4 into, so the total height capital H sorry guys, into, so again small h is 4 is equals to 2 into, so root over, the second hole is made at a height of 6 into, so the total height h minus 6 I am writing. So 2 gets cancelled. So then squaring on either side we get 4h minus 16 is equals to 6h minus 36, right? So then, so bring this 4h to that side. So 6h minus 4h is equals to, bring this 36 to this side. So 36 minus 16. So we get 2h is equals to 20, h is equals to 10 centimeters. So the total height h is equals to 10 centimeters. So they are made at a heights of 4 centimeter and 6 centimeters. So you can also derive the general formula for this. So let me do that also. See here. So we can also derive the general formula for this. So if the range is same, if so the range is same for two holes, for two different holes, so then the R1 is equals to R2. So let's suppose the first hole is made at a height of, so this is a container, so in which, so the fluid is filled up to the brim, let's suppose. So then there are two holes made. So one is at a height of, here is one at a height of h1. So the other hole is made at a height of h2, let's suppose. Okay, so let the total height of this container is capital H I am taking. Done. Chala. So let's apply the general formula. So from this, the fluid is these two fluids are striking the same point. So which is the range is same. So R1 is equals to R2. So then we can write the formula. So 2 into root over. So the first hole is made at a height of small h1 into. So the total height is capital H minus small h1. Yes, which is equals to. So 2 into root over h2 into. So the h minus h2. Done. So 2 gets cancelled. So squaring on either side we get h1 into h minus h1 is equals to h2 into h minus h2. That's it, right? So then I can write h1h minus h1 square is equals to h2h minus h2 square, right? So then, so let's send this to that side. So we get h1 square minus h2 square is equals to h1 square. I am sending it to that side. So then this part you send it to this side. So yeah, so h1h minus h2h, right? So then, so let's do the simple calculations. So h1 square minus h2 square. So I am writing it as h1 plus h2 into h1 minus h2, which is equals to, so here I am taking capital H common. So if you take capital H common, again we left with h1 minus h2. So h1 minus h2 gets cancelled. The total height will be equals to h1 plus h2. So this is a trick for the last question actually. So that means if the two holes are made at two different heights, h1 and h2, if their range is same, the rate of the liquid which is coming out, so is pointing at the, so it is falling at the same point. So then the total height of the container will be, so the individual sum of the individual heights of the two holes. So that's what in this question you can directly write 6 plus 4, 10 is the correct answer. So you need not to do these calculations. So this is a general concept. Done guys? Understood everyone? Chal, good. So next. So then maximum range. So in the projectile motion he has studied. So what is the maximum range formula? So what is the maximum range? When the maximum range will come? So the range formula that we know is equals to 2 into root over h into h minus h. Right? So the range will be maximum when the range will be maximum if dr by dh is equals to 0. The range will be maximum if so the dr by dh is equals to 0. So then, sorry, not I wrote total h. This is small h with respect to the height. So then we get, so the height h is equals to from here, so the h by 2. So that means if the hole is made at a height exactly, so half of the total height, so then the range will be maximum. So what is that maximum range you can find, right? So that R max is equals to, so in place of 2 into, in place of small h we can write h by 2. So into capital H, let it be, in place of small h write again h by 2. So 2 into, so root over h by 2 into, so what is h minus h by 2? So again h by 2. Done. So here 2 into, so 1 h by 2 gets cancelled. So 2 gets cancelled. So h. So that means the R maximum, the maximum range is equals to, so the total height of the fluid. So the maximum range is equals to total height of the fluid. So when it will occur? When the hole is made at a height h by 2. Done guys. So these are all the general results you should remember. Clear? Chalo. So then what is the time taken to empty the tank? See here. So this is a vessel. First, let's suppose this vessel is filled up to the brim like this. So to empty this tank, first where should the vessel hole has to be made? Obviously at the bottom. So whose cross sectional area is small a. So then, so the fluid comes out from this with a velocity v. So to empty the tank, so the first thing is, so the hole has to be made at the bottom. Hole has to be made at the bottom of the vessel. At bottom of vessel. Done. Chal. So then here the cross sectional area, let it be a, and here the cross sectional area small a, and with what velocity? So the water will come out or the fluid will come out. So with v is equals to root 2gh, right? So now we need the time taken to empty the tank. So just you can remember the direct formula. So the time taken t is equals to, so the cross sectional area at the open tank by a into, so root over 2gh by g. Root over 2gh by, sorry, root 2, sorry, my bad, root 2h by g. This is a formula you guys should remember. Done guys? Clear? So everyone, so directly you should remember the formula. So again I'll write here. So the time taken is equals to a by a into root over, so 2h by g. So what is the capital A? So the cross sectional area here, and small a, the cross sectional area of the orifice or hole, and then what is capital H? So the total height of the fluid. Done. So if you observe here, so the time taken to empty the tank is directly proportional to root h. So the time taken to empty the tank is directly proportional to root h. So remember this one also. This is also the important relation. So just note down this formula everyone. Note down this formula. Done? Chal. So generally this cross sectional area like this you can write. So let's try this question. So what's the question says? A rectangular vessel when full of water takes 10 minutes to be emptied through an orifice in its bottom. Okay, fine. So then how much time will it take to be emptied when half filled with water? So fine. So when it is completely filled, so it's taking time 10 minutes. So when it is half filled, so let its total height be h. So the h1 is equals to h, and then so let the h2 is equals to h by 2. So here the time taken, let it be t1, which is 10 minutes. So then, so what's the time taken in this case when it is half filled? So the simple concept, we know that the time taken to empty the open vessel is directly proportional to root h. Done. So then you can write the formula. So t1 by t2 is equals to root over h1 by h2. So then I can write, so that in the first case it's taking 10 minutes time. So t2 we have to find. So and then, so in the first case the total height is h. So and in the second case the height is going to be h by 2. Done. So the answer we got, so which is 10 by t2 is equals to, so this h which gets cancelled, root 2. So from here t2 is equals to 10 by root 2. So we have got, so 10 by, so what is root 2? 1.414. So approximately 1.5 I'll take. So 1.5 means 3 by 2. So which is something around 20 by 3. So which is 6 minutes, 6 point something something. So which we get 7 minutes approximately I can take. Done guys. Clear? So approximately 6.7, 6.8 something like that we get. So which is nothing but, as I am taking this as 1.5. So you can increase this value to 7. So option 2 is the correct one. Done. Clear? Sure. So now let's take the next question. So try this question. Try this question on your own. A tank is filled with a liquid up to height h. A small hole is made at the bottom of this tank. Consider t1 be the time taken to empty the first half of the tank. Okay. So and t2 be the time to empty the rest half of the tank. Okay. So then determine t1 and t2 ratio. So let's see here. So first, so this is a container, open container. A tank is filled with a liquid up to height h. So height h. So now, so to compare, a small hole is made at the bottom of this tank. Consider t1 be the time taken to empty the first half. So first let's suppose the total time taken, let it be t. So now the total time taken will be equals to t1 plus t2. So t1 is the time taken to empty the first half, t2 is the time taken to empty the second half. So now I need t1 by t2 ratio. So I am taking total time, and then when it is already half emptied, so to empty the remaining half, it is taking the time t2 in this case. It is taking time t2 in this case. So here the total height is h, and here the total height is h by 2. Yes or no? So here the time taken is t2. Done. So here the time taken is t. So now I know that t is directly proportional to root h. T is directly proportional to root h. So now what I am doing is, so let's write t by, so the time t2. So the t by time t2 is equals to root over. So in this case the total height of the fluid is h, right? In the second case, so the total height when the time is t2, when the time is total time is t, the total height is capital H. Yes. So when the total when the time becomes t2, so the total height is h by 2. So that's it, done. Again, so we have got, so t by, t is nothing but t1 plus t2 by, so t2 is equals to, So root over, so this is h gets cancelled, so 2 root 2. So then done. So I can write, so T1 by T2 plus, so T2 by T2, so is equals to root 2. So I need T1 by T2 ratio. So then T1 by T2, so plus 1 is equals to, what is root 2 value? 1.414. So then I can write, so what is T1 by T2 here? So the T1 by T2 is equals to 1.414 minus 1. So which is 0.414. That's it. 0.414. So option 4 is the correct one. See, you can't take the T1 time because we don't know what is that height. Right. So that's why I'm taking for the complete emptying the tank, and next, so the half, so that you can easily get the answer. Done, guys. Clear? So now the velocity of efflux in closed container. See, in the open container, so the pressure P1 is equal to P atm, but here the pressure is not P atm. So here the pressure is somewhat P. Okay, so let it be the 0.1, let it be the 0.2. Again you can apply the Bernoulli's principle. Again we can apply the Bernoulli's principle. So here first, so this is the first point, this is the second point I am taking. So the first point P1 plus, so this what is the velocity there? So half rho. So let the velocity here it be v1 square. V1 square plus it is at a height h. So rho g h. Rho g h. And consider this is the baseline. Consider this is the baseline. Okay, so that this height will become 0. So the second hole, so this height will become 0. So I can write this height as 0. So which is equals to, so the next one, the P2 pressure plus here, so the velocity, so half rho, so the velocity let it be v2 square plus it is at a height h. So rho g h. Right? So then I can write here, so what is P1? P1 is nothing but P atm plus, so what's the velocity there? Half rho v1 square is equals to, so here the height will become 0, so that's why this I am considering 0. P2 plus, so this part I can take it 0, so because the velocity v2 is equals 0, so this comes down very slowly, so the velocity we can take approximately 0. So this is rho g h. So then you can find the velocity in this case. So just you get the equations this side and then so find the concept. So can you guys do these calculations? So where the pressure will be more first? Here the pressure is there and here the pressure is there. So here the atmospheric pressure and here some other pressure. So let's write this way. So P2 minus P atm. P2 minus P atm. So I brought it to this side. So then you can bring it to this side. Half rho v1 square minus rho g h. Right? So then you have to find what is the velocity v1 there. So you can find the velocity v1. So do that calculation on your own, everyone. So do that calculation on your own first. So just you have to find what is v velocity there. That's it. Do the calculations now. So the P2 minus P atm. So what we got? Done, everyone. So half rho v1 square. So just take the LCM there. So 2 is the LCM. So we got rho v1 square minus 2 minus, so 2 rho gh, right? Done. So fine. So I need the velocity v, actually v1 velocity. So P2 minus P atm is equals to, so then I can write here, send this 2 to this side, so this becomes into 2. So send this root gh also, then rho V1 square. So then V1 square is equals to, so 2 into P2 minus P ATM plus rho 2 rho GH by rho. So done. So then the velocity V1 is equals to square root of, so 2 into P2 minus P ATM plus, so 2 rho GH by rho. So that's it. Or else, so you can also write it as, so split the rho to both the terms. So the velocity V we can write as square root of, so 2 into P2 minus P ATM, P2 minus P ATM. So this is not that important. You can just follow the procedure. So no need to remember the formula here. So plus this becomes rho gets cancelled, 2GH. So here actually compared to this value, so this 2GH value will be very small. So this 2GH will be ignored most of the cases. So this 2GH value will be ignored. Clear? So done. So no need to remember the formula. So just understand the concept. That's it. So have a look at this one. So just have a look at this one. I'll just have some water. See, here if you substitute, if it is an open tank, for open tank, so you can take that P2 as PATM, P2 as PATM. So then what happens? So here PATM cancel, this whole term will become 0. Again we'll get the root 2GH. So the velocity V1 will become root 2GH again. Done, guys. So this root 2GH it will be neglected in the closed container because that value is going to be very small. Done? Good. So this is done. So we have, so then we have some applications here. So what are the applications of this velocity of efflux? So blood flow and heart attack. So for the NEET students, so they know very well. So whenever we eat more oil items, so the cholesterol will be formed in our body, right? So actually heart supplies blood to our all the other parts of the body. So for the rest of the body, heart supplies blood through arteries, right? So through arteries. Chalo. So now, so these arteries, so are the tubes. Arteries are nothing but tubes. So in which, so the blood flows. So now whenever cholesterol forms in the body, so what happens here? So you can observe, so this is a cholesterol. So cholesterol plaque buildup. So here some part of the artery is blocked with the cholesterol. So now for the blood flow, so the blood flows from here. So when the blood is coming from this cross-sectional area, the velocity will be, if the cross-sectional area is more, so the velocity will be less. So wherever the cholesterol is formed, so at this point, so the cross-sectional area is less. At this point, the cross-sectional area is less. So the velocity will become more. The velocity here will be very high. The blood will have more velocity here. So if the velocity is more here, so the pressure will be less. So inside the artery, so the pressure is less, and outside the artery, so the pressure is going to be PATM. So yes or no? So now, so the outside pressure is greater than the pressure inside the artery. The pressure inside the artery. Yes or no? So then what happens? So the burst. So this is heart attacks or all the heart related issues. This is the concept, guys. So where the outside pressure will be more and inside pressure will be less. So what is the physics in it? So here the cross sectional area is more in here, so the velocity will be less, so that pressure will be more, the atmospheric pressure and plus pressure, so they both will be same. But here what happens? So the velocity will be more. So the area is less, the velocity will be more, the pressure will be less. And then the pressure outside is more and the pressure inside is less. So the blood clots blocks artery. So here the blood clot, so which blocks the artery. So the blood supply will not takes place. So this is a reason for the heart attack. Okay, so the physics involved in it is this one, the pressure, area, velocity concept. Done, guys? Chalo. Good. So now, so the aerofoil or lift on aircraft wing. So this we already discussed. So consider this is a aeroplane wing. So the at the top, so the velocity v1, at the bottom, so the velocity v2. So this velocity is more and then this velocity is less. At the top of the aeroplane wing, the velocity is more. So that means the pressure is less. And then at the bottom of the aeroplane wing, so the velocity is less. So the pressure will be more. So overall, so there will be some upthrust. So or the force. The upthrust or the force on wing. Force on wing. So what is that force or upthrust on the wing? Which is the change in pressure into area. So delta P into area will give the force on the wing or upthrust. We solved the questions related to this in the last session also. Done. So this is also one of the concept related to, so the Bernoulli's principle or the velocity of efflux. And then we have one more effect, so which is based on this fluid mechanics, that is, so Magnus effect. So swinging of ball. Swinging of ball. Right. So hope you guys watch cricket. So in the day before yesterday also, Australia versus India match. So where Ashwin got 3 wickets, 3 or 4, 3 I guess. So at the right time he got 3 wickets. Warner and some other, he took the wickets, right? So how the ball swings, swing or spin, how the ball swings or spins. So there is also the physics involved. See here, if the ball is spinning, see it rotates. So they release the ball like this, right? So when the swing or spin takes place, they release the ball like this. The ball rotates. Now, so at the topmost point of the ball will have, let's suppose, so this has the velocity of center of mass. And then, so this point will have velocity of center of mass plus r omega, right? And then here the velocity of center of mass minus r omega, because so the r omega here at this point will act in this direction, right? Here the r omega will be in this direction. So VCOM plus r omega, this we studied it in the rotation, and here VCOM minus r omega. So now overall the relative velocity with respect to the wind, here more, here the relative velocity of the ball with respect to wind, is more here at the top surface, and here the relative velocity is less here at the bottom surface. So the relative velocity is less at the bottom, right, with respect to the wind. So now, so here the velocity is more and here the velocity is less. As a result, the pressure here, the velocity is more, the pressure here it is less, and here the velocity is less, the pressure here it is more, right? So there will be some force which acts on it. So there will be some upthrust or the force which acts on the ball, because there is a pressure difference. There is a pressure difference, right? So at the top, the relative velocity of the ball with respect to the wind is more, and at the bottom, so the relative velocity of the ball with respect to the wind is less. So here velocity is more, pressure less. Here the velocity is less, pressure more. So the bottom pressure is more. As a result, what happens? So there is some upthrust or the force acts. The force on ball here. The force on ball acts. So as a result, the ball swings more. Understanding? So here in this also you can see here. So this is a crowded streamlines. Crowded streamlines. So the velocity more, right? So here, so less crowded, so the velocity less, so pressure more here, and then pressure, less here. So as a result, the ball swings. Clear? This effect is called actually the Magnus effect. Done, guys? Clear concept, everyone? Chalo. So that's it from my end for the today's session. So this is about the fluid mechanics. So in the next lecture we'll start the new chapter. So till then, keep studying. All the very best. Bye.